Hi, in this video we'll be going over the high frequency response for amplifiers. Let's get started. So we're going to be covering high frequency response for an amplifier. As we've seen, an amplifier has some sort of response that would look something like this. Perhaps it has a low frequency zeros. It would have a low frequency cutoff, which would be defined by omega L. In some cases, omega L goes all the way to 0. So omega L can go all the way to DC. And in that case, the low frequency response would look something along here. So it can be either here or here, depending upon whether there's a 0 at DC or not. As we get into the midband region, which is where we're more interested, then the midband region would look something like this for an amplifier. This is the gain, by the way, for an amplifier, V out over VI. And we're plotting this versus frequency. So as we go higher in frequency, eventually we'll reach a high frequency cutoff point, which we'll define as omega sub h. So we want to, in this video, go over how to find or estimate the value for omega h. And that is typically given by the lowest high frequency pole, or it's a combination. If the poles are close together, then you can use a formula to estimate what omega h would be. If the poles are fairly widely spaced, then it's the lowest high frequency pole. So the lowest of all the high frequency poles. So this words here just mention what we just mentioned. Omega L is a low frequency cutoff, and it could go all the way down to 0 radians per second. But in this video, we're more interested in omega sub h, and that will be our high frequency cutoff. Now this cutoff is typically due to parasitic capacitors. They're inside either transistors or the wiring capacitance of a circuit. And so these extra capacitances, which are typically unintended, cause the high frequency cutoff. Now sometimes you want that high frequency cutoff to be lower than what the parasitics might give, and you might add intentional capacitors in order to reduce the high frequency cutoff if you find that there's high frequency noise that you want to reduce. This analysis will work in either case. Now what we want to use is use the open circuit time constant approach in order to estimate our omega h. So we'll start by looking at a common source amplifier, shown here. So we have a common source amplifier, an NMOS transistor. In this particular case, it will have some low frequency capacitors, C sub C1, C sub C2, and C sub 3. Are all low frequency capacitors which are used to just make the biasing easier. So we can bias this circuit, so the amplifier itself is really here, and we just want to not worry about what our DC bias is for our input or what the DC bias is for the output. So we use capacitors to couple between them and just make our life a little easier. In many circuits, as I mentioned, you won't need any of these DC coupling capacitors, and so it would just operate all the way down to DC. But in this case, we have these DC coupling capacitors, but at the frequencies that we're interested in, all three of these capacitors will just look like short circuits, and we can just imagine they're all short circuits because we're looking at the high frequency performance of this amplifier. So that just is mentioned down here. They're all low frequency coupling capacitors and bypass capacitors, and so they'll all be shorted for our high frequency analysis. So if we draw the small signal model for this, we'll have a circuit that looks something like this, shown here. We have these transistor capacitors, the gate to drain capacitor of the transistor, the gate to source capacitance of the transistor, the drain to bulk capacitance of the transistor, and also we have the load that we're having to drive for this amplifier. So that load is just this load up here. Because we'll have some output load, we have to drive another stage, and that stage itself will have some input capacitance associated with it, which we need to include when we're looking for the high frequency performance of this amplifier. So now first we can look for the midband region. If you recall, we said the midband region was this region up here. So we'd like to know just what the gain is before we reach our high frequency cutoff. So in this particular circuit, we just would open circuit all our high frequency capacitors. So all of these then become open circuits. We just make them all opens. And we find the gain for this circuit here. And we find that the gain in this case is just going to be V out divided by VGS. So the gain from the output to VGS at this point right here. And that'll just be minus GM times the impedance seen at this node here, the output node. So we'll just define, to make our life a little easier, is we'll define R sub L prime to be equal to this resistance here, which is the output resistance of the transistor, the load resistance that we're driving, and that drain resistor in the top. So the drain resistor in the top of the common source amplifier. And of course there's a minus sign here because it's an inverting amplifier. Now, the problem we have with this circuit that we have here is we like to find the poles at the different nodes. We'd like to find a pole associated with the node right here and a pole associated with the node right here, but we have this extra capacitor that's going between those two nodes. So this is where we can use the Miller theorem to break up this capacitor into two capacitors. To break up this capacitor into two capacitors, one over here and one over at the right side, and then we can eliminate this one over here. So we'll use the Miller theorem for that. What we have is we'll break CGD up, as I mentioned, using this Miller theorem. And so that then ends up being, we have this extra capacitor here, now C sub M1, and we also have another capacitor here, C sub M2. And using Miller theorem, we know that C sub M1 is equal to that gate to drain capacitance times 1 minus the gain, the midband gain. Now in this case, the midband gain is minus GM times RL prime, so it becomes 1 plus GM times RL prime. So that's this was for C sub M1, Miller 1. On the other side, we have C sub M2, and C sub M2 will be again the gate to drain capacitance, but in this case it'll be 1 minus 1 over K. So 1 minus 1 over K, again we have a GM, the gain is minus GM RL prime, so it becomes 1 plus 1 over GM RL prime. Now in the case that GM RL prime is much greater than 1, so it was say 10 or 20 or so, we could approximate this Miller capacitance as just the C gate to drain on the right hand side. So we could say that this over here, CM2, would just be approximately equal to C gate to drain, but we can't do that on the left side. On the left side, we actually have that C sub M1 is the gate to drain multiplied by this extra term here, 1 plus GM times RL prime. So now that we have this circuit, the C gate to drain capacitor broke up into two sides on either side, we see that we now just have a capacitor over here, which is combined, so CGS plus CM1, and that will create a pole, a high frequency pole, and then we have a capacitor on the right hand side, which is these two capacitors combined, which create another high frequency pole. So this circuit has two high frequency poles. To find the pole frequencies, we just have to find the equivalent resistance looking that this capacitor would see, and the equivalent capacitance, or sorry, the equivalent resistance that this capacitance would see. So for omega P1, start off with this one. So the first one, we'll say this capacitance plus CGS plus CM1, so we have this capacitance, multiplied by the equivalent resistance it would see. In this case, it would just see R sub signal in parallel with RG. In other words, it would see coming up here, ground and ground, because we zeroed our input voltage. So we see RG in parallel with R sub signal to get back to the other side of the capacitor. And we take, multiply those two together, so R times C, take the inverse of that, and that becomes our pole frequency in radians per second. and that would also equal 2 pi times our pole frequency in hertz. We're calling that omega equals 2 pi f. If you want to look for omega p2, so the pole due to this side on the right, we have that these two capacitors again are combined, they're in parallel, so we just have C sub the drain to bulk of the transistor plus CL plus CM2. CM2, if you recall, we said was approximately equal to C gate to drain. If we're assuming GM RL prime is much greater than 1. If not, then we would leave it as this term over here. We would just leave this term over here. But in this case, we'll assume it is much greater than 1. So we have CGD approximately for CM2. Multiply that by the equivalent resistance it sees, and the equivalent resistance it just sees is RL prime up here. So we have that this becomes the equation for the second pole, and raised to the -1. And again, this would be what the pole frequency would be in hertz. We would divide by 2 pi. So we basically now have found that we know our mid-band gain is equal to minus GM RL prime. We know we have two poles, so we can write it as divided by 1 plus S over omega P1, and also divided by 1 plus S over omega P2. Of course, that's the gain from the gate to the output. So we also have a resistor divider in our circuit, which is RG divided by RG plus R signal. So just going back and seeing that, that was up in, right from here, from this point to this node here, VGS. So the gain from V signal to VGS is RG divided by RG plus R signal. So this becomes our overall gain given by V out divided by V signal. Now, as I mentioned, we have two approaches to find what omega H or FH would be. One, we could say if we believe that one of our poles is much lower than all the rest, if we do the analysis and find that to be the case, then we would say that FH would be either FP1 or FP2, whichever is the lower of the two, because that would be the case where it would start to drop first. So that's sort of the dominant estimate. We just decide which is the lowest of them, assuming that they're widely spread apart, and then that becomes our high frequency cutoff. If they are not that widely spread apart, then we can use this approach and say that the cutoff is equal to 1 over FP1 plus 1 over FP2, and take the whole thing to the inverse, which is sort of the mathematical equivalent of putting them in parallel. So in other words, if I had a high frequency pole at 1 gigahertz and another high frequency pole at 1 gigahertz, that would be equivalent to having a single high frequency pole at 1/2 of 1 gigahertz, which would be 500 megahertz. So we'd estimate it as that. Now what you find is that normally omega P1 is lower than omega P2. Omega P1, if you recall, is due to the pole on this side here. So we have a pole due to this node, and we have a pole due to this node. So normally, let me just write that out. We think of omega P1 occurring here, and omega P2 occurring on the right-hand side here, omega P2. Omega P1 often dominates because, as we mentioned, we're taking a capacitor here, C gate to drain, and it's multiplied by the gain of this stage from the gate to the drain. And if that gate to drain amplification is 20, then this is taking this capacitance here and multiplying by a factor of 20, which can often make this to be the dominant pole side, because we have one transistor which might be multiplied by 20 times its value. So often you'll find that omega P1 can be lower due to the effect of the Miller effect on the gate to drain capacitance. one way to try not to have that so it's not the case is you can reduce the gain, but of course that might go against what you're trying to build. So the other way is you can keep omega p1 high, so not to have it go too low, is if you can reduce R signal. So if you recall, if we go back to omega p1, it was multiplied by R signal in parallel with RG. Well, RG is generally a large resistor in order to set up biasing, but R signal you can make small. And if you recall, our signal is basically just our output impedance of our previous stage here. So if we can somehow require that the previous output stage has a very low output resistance, then we can keep the pole due to this node to be small. So let's look at that for a second. Let's make the assumption that our signal is equal to 0. And let's find the high frequency cutoff and the unity gain frequency for this amplifier. So our FT will define as a unity gain frequency, so the frequency where the gain goes to 1. And we'll make the assumption that GMRL prime is much greater than 1. So the gain from the gate to the drain is much greater than 1. So what we know is that omega p1 is no longer the main dominant pole. In fact, it would be very high frequency now, since if our signal goes to 0, omega p1 will go to infinity. So what we'll find is that omega p2 now is the dominant one, and that is just given by this equation here. The capacitance of the drain to bulk plus the load capacitance plus the gate to drain capacitance. Again, we're letting the Miller effect makes the output capacitance approximately equal to the gate to drain capacitance, and times RL prime. Now the low frequency gain we have is just minus GM times RL prime. And again, we're going to ignore the resistor divider in the first stage because we've made our signal equal to 0, so that no longer becomes a resistor divider anymore. So that we can assume that the gain is equal to 1. Now we have a single pole, a low frequency gain, which is much greater than 1, so AM is much greater than 1, and so this becomes a single time constant transfer function. So we know from before that the unity gain frequency for that, if I know the DC gain and I know the 3 dB frequency, I just multiply those two together, and that's approximately equal to the unity gain frequency when the DC gain is much greater than 1. And that is the case that we're looking at here. So we have the unity gain frequency is equal to the DC gain A sub m times FH, the high frequency pole. If we multiply those two together, so we're multiplying this value here times this here, what we see is that the RL primes cancel out. And so the actual unity gain frequency is just given by GM divided by this capacitance here, C sub drain to bulk plus C load plus C gate to drain, and the 2 pi factor is just to change from radians per second into hertz. So what's interesting here is that the unity gain frequency is now independent of RL prime. So then you say, well, what would happen if I changed to RL prime? Well, we plotted that here. So if our original one with RL prime was given by this curve here, so this would be with RL prime. And let's say I changed it to a new value of RL prime. So I changed it, so I'll call it RL double prime. So we'll have a new value. And let's say it's a lower value, then the DC gain would reduce. The omega H would move to omega H sub double prime, but it would then still follow pretty much the same curve, and this omega T here stays the same. So basically changing RL prime just changes where this break is, but they all follow the same curve here, and they all cross 0 dB. This is the 0 dB location at the same frequency. So omega T is independent of RL prime. Of course, the 3 dB frequency is changing with RL prime. So we have this result that this is our unity gain frequency, and that's independent of RL prime. So we looked at the common source amplifier. Now we'd like to look at a Cascode amplifier. So let's just revisit our common source amplifier, but make a simplifying assumptions just to see how that compares with the Cascode amplifier. So we're going to revisit our common source amplifier in this circuit right here. But the difference now is we're going to assume that we only have one capacitor in the whole circuit, and that is CL, just to make our equations a little bit easier to work with, so we don't have to worry about the Miller effect and things. So we'll assume this transistor is a capacitor-free transistor, and that C sub L is limiting our high-frequency performance. Things would work almost the same if I didn't make this assumption, but we'll see this in a second. So in this case, what we know is that the DC gain for this is going to be minus GM times R out divided by 2, where we're assuming that the impedance looking into our transistor here is R out, and the impedance looking up into this current source is also R naught. Sorry, I meant to say R naught, not R out. So it's R naught looking down and R naught looking up. So that means that our total impedance looking into the output node is R naught divided by 2. So that's given by this value here, and it's multiplied by the GM of this transistor here. So that becomes our DC gain. We also know that our 3 dB frequency, in this case, will just be given by the CL transistor, or sorry, the CL capacitor here, and we find the impedance, or the impedance that this, the resistance that this capacitance would see, and that's just going to be the impedance looking into the left, which will be R naught divided by 2, and back into the ground node. So it'll be R naught over 2 as well. So that becomes a 3 dB frequency. And if we multiply those two together, because we assume that GM R naught over 2 is much greater than 1, that gives us our unity gain frequency. And so the unity gain frequency is GM divided by 2 pi divided by CL. Okay, so nothing too new here, just a simplified version of what we saw before. But now let's look at the Cascode amplifier case. So now in this case here, we'll say that the impedance looking up is now given by GM R naught squared, because it's a Cascode current here. We also have that the impedance looking down, R naught, capital R sub naught, is also approximately equal to GM R naught squared, because it's a Cascode device. You're looking through the M2 to the drain of M2, but we also have M1 in series with that. So we have that the DC gain is going to be it will be minus GM of M1 transistor, but times the impedance that we see at this node here, which will be GM R naught squared in parallel with GM R naught squared. So we'll have a GM R naught squared divided by 2, but times GM, so the whole thing ends up being GM squared times R naught squared divided by 2. So we've seen that our DC gain has been increased by GM R naught, because we have a Cascode transistors M2, and also we've cascoded now our current source as well. Our 3 dB frequency now is going to be, again, the capacitance we see here, and we find the resistance that we'd see across it, which is going to be the resistance looking back into this node, which will be GM R naught squared divided by 2. So if we go through this, we'll see that CL divided by GM R naught squared divided by 2. Now, if we multiply these two together to get the FT, remember again, if we assume that the DC gain is much greater than 1, which is the case here, then the DC gain times 3 dB frequency will approximately equal the FT. So multiplying these two, multiplying multiplying this times this value. We ignore the negative sign here because we just multiply the magnitude of the DC gain times the 3 dB frequency. That will give us our unity gain frequency, which works out to be just GM divided by 2 pi divided by CL. If we go back and look at the previous case, it's exactly the same. So we've got the same unity gain frequency as we had in the previous case. So it's unchanged. So if we look at the Cascode case here, with a Cascode amplifier, we see a very large DC gain and a fairly low 3 dB frequency. With the common source without being cascoded, we see a lower DC gain, but a higher frequency, 3 dB frequency. But as they drop off, for both cases, we have the same omega t. So the unity gain frequency doesn't change, but we get a larger DC gain and a lower 3 dB frequency. So that's a Cascode amplifier. So we haven't extended our bandwidth from a unity gain frequency point of view, but we have a much larger DC gain. And so in many applications, that's a lot of value, particularly in the feedback loop. Then having a much larger DC gain will make the very, very low frequencies more accurate with some feedback going around the entire system. So this just summarizes it, that if in a Cascode amplifier, if your output capacitance load determines F sub H, then our Cascode amplifier has the same FT as the common source amplifier, but a higher DC gain and a lower 3 dB frequency. Now, this gets a little bit scary. What we're looking at here is the small signal model, where I've just left the transistors as transistors. We know how to work with those as small signal models. So we're not showing the bias conditions at all here, but we're now showing all the capacitors. So we're showing we still have the C sub L, and now we'll include all the other capacitances. So what we also have is the gate to source capacitance of 1, the gate to drain capacitance of 1, the drain to bulk capacitance of 1. So we add the 3 extra capacitors for M1 here. Then we also add the 3 extra capacitors for M2, which will be the gate to source of M2, the gate to drain of M2, the source to bulk, actually I guess it's 4 extra capacitors in this case, the source to bulk of M2, so the capacitance here to ground, and finally the drain to bulk of M2. So there's 4 capacitors in this case, the source, drain, gate to source, and gate to drain. Now you may ask, well, why was there not 4 in the M1? Well, there is another capacitor here, the source to bulk capacitor for M1, but it's from ground to ground. So this would be source to bulk of 1, but it's going from the ground to ground, so we really can ignore this capacitor. So there's 4 as well for that transistor. Now, so this looks like a lot of extra capacitors, but really it's not as bad as it seems. Because what we see is we see first off that CL is just in parallel with C drain to bulk. Also, this is a small signal ground over here for the gate of M2. So the gate to drain of M2 is also in parallel with C sub L. So all 3 of those capacitors are just in parallel. So that just changes our load capacitance. We also have a capacitor at this node, this intermediate node, but that will also be in parallel with this capacitor here, because this again is just a grounded node at this point. So, and this is already a grounded node, so the only one we really have to worry about from a Miller effect is this capacitor right here, the gate to drain capacitance of 1. So if we define K to be the gain from VG1 to V1, So we define that to be our gain because that's where we see a Miller capacitance, and that affects, we can then break this one capacitor up into two capacitors and make them both grounded. But what we notice though is the gain typically from the gate 1 to V1 is much smaller than it would be in a common source amplifier. In a common source amplifier, it's actually the gain that you're trying to get. In this case here, it's the GM of M1, but times the impedance that you'll see at this node. The impedance that you'll see at this node is the impedance looking up in parallel with the impedance looking down to into the drain of M1. Well, the impedance looking down into the drain of M1 is RO1, which is large, but the impedance looking up into M2 is looking up into the source of M2. At frequencies of any kind of interest, the drain resistance of M2 starts to become small, so the impedance looking up just looks like 1 over GM2, which is much smaller than R out, or R naught. So the impedance looking up is about 1 over GM2, which is a small value. So you find that the gain from VG1 to V1 at low frequencies, or even at moderate frequencies where the capacitances over here have started to have some effect, is just minus GM1 divided by GM2. So the gain here is not a minus GM R naught, but a minus GM 1 divided by GM2, which is typically small. That's maybe perhaps 1. So you see very little effect here because we get very little Miller effect because the gain here is not large. Now there would be potentially a Miller effect on C gate to drain of 2. So if you were somehow came along and you injected a signal over here, then the gain from here to here you'd think might be large. But for a couple of reasons it's not. Number one, this is not a grounded node. From a small signal point of view, there is no signal here. So it's a small signal ground, so we don't have to worry about the gain across CGD2. Also, this is M1 here is already making it so the gain from the gate of M2 to the output is not that high. So if you work out the actual gain, it's been effectively resistor degenerated, and so there's a fairly small gain from the gate of M2 to the output. So that doesn't really affect things. So what we have is we have this system here. So we now have, rather than just 2 poles in the system, we now have a capacitor at the output, CL prime, capacitance at this intermediate stage, which we can define as being C sub D1, and a capacitance at the input stage, which is shown over here. Now, let's look at each one of these individually. So those create 3 poles in our system. So let's start off with CL prime. CL prime will be C gate to drain of 2 plus C drain to bulk of 2 plus the load capacitance that we have here. Going to the next one, we have the C drain of 1, which will be the drain to bulk capacitance of M1 here. It will be plus, so that's the drain to bulk of M1, plus the source to bulk of M2, so plus this capacitance here to the bulk connection, or to ground, plus 1 minus 1 over K times C gate to drain of 1, so it's the Miller effect for the gate to drain here, and plus C gate to source of 2, which is the capacitance over here, and that's connected to ground on one side. So all those make up C drain to 1, and then finally we have also this capacitance here, which we'll call it CG1, C of the gate to 1, and that's just going to be the gate to source capacitance of M1, which is here, plus the gate to drain with a Miller effect, where it's 1 minus K times C gate to drain of 1, where C gate to drain of 1 is up here. So, but what we said is that K is V1 over V sub gate 1, and that's not a large number in this particular case. So we won't get a large Miller effect happening here. Now, if we find the R equivalent for these three different resistors, we have for CG1, for this one here, that will just see an impedance looking over here, which would be R signal. The impedance looking over here is infinity. Looking to the right, and so we'll just see infinity in parallel with R signal, so it's going to be R signal. So that's the equivalent resistance for CG1. The equivalent resistance we see for CD1 will be the impedance looking into this node, into the drain of M1 and to the source of M2. And it's going to be dominated by, because it's in parallel, so it'll be the impedance looking down, which is approximately R0, and the impedance looking up, which is approximately 1 over GM2. So it's just going to be approximately 1 over GM2. Now this does depend upon RL. So looking up into this resistance up here should actually be written as 1 over GM2 plus RL divided by GM2 RO2. But assuming that RL is not that large, then we can approximate this as just 1 over GM2. Or in the case where RL is quite large, if it's also GM R0 squared, then at a bit higher frequencies, we'll see that this capacitance comes into play, so the impedance starts to look lower, in which case this impedance starts to look lower, and it still gets dominated by this impedance here, because this gets divided by GM R0 as well. So in both cases, we find that this ends up being the impedance roughly that sets the pole frequency for the capacitance at the drain of M1. So finally we have that the last one is this capacitance over at the right here, CL1, and we see that just looks like the impedance that we see looking to the right here, which will be RL in parallel with GM R0 squared. So in parallel with the impedance that we see looking down through here. And almost always this will dominate. This times the output load capacitance, and this is such a high, normally RL is also very large. So in most cases when you're using this circuit, the load that you're driving is also very large, in which case the whole thing becomes proportional to GM R0 squared. And that is a very large impedance, in which case multiplied by the capacitance at that node, it tends to dominate. So what we find is that tends to be the lowest frequency pole and dominates the overall circuit. So the Miller effect doesn't come into play here because of our gain here not being that high. So that's the big benefit of using a Cascode amplifier, is to get around the problems with the Miller effect. Okay, so now we've looked at the common source amplifier and the high frequency response for that. We also looked at the common gate amplifier because that was really the Cascode portion of a Cascode amplifier. So common gate amplifier was the Cascode part of that, and that was the high frequency response for that. So finally, we'd like to look at the common drain amplifier. So that's our last sort of amplifier type, and in this case, it's also referred to as a source follower. So it's a source follower because the source is following the gate. It's approximately a gain of 1 typically. So first, we should recall what we used for the model for a common drain amplifier. So we have our common drain amplifier here. If you recall, we would typically take a R sub D up through this, And we would replace this, where this is VG and VS. And we replace this with a ideal open circuit voltage, VOC, a resistance R sub X, and VOC would be equal to VG, and Rx would be equal to 1 over Gm of the transistor plus R sub D divided by Gm R naught. Now in the case that we're looking at, RD is equal to 0 because there is no RD placed in this. So RD is equal to 0. So in this case here, then we actually have the Rx. We can ignore this. This goes to 0. So Rx just becomes 1 over Gm. Write that out a little bit better for you. Becomes just 1 over the Gm of the transistor. And that becomes our model. This becomes this VOC is equal to VG, where this was equal to VG. The input of the gate voltage. So it just becomes, and whatever we're driving this with then, if we're driving this with R sub L, it just becomes a resistance divider to get the output voltage over here, would just become RL divided by RL plus RX times VOC. And VOC is just equal to VG. So making use of this, we see up here that we have exactly that configuration. So this is a common drain amplifier. And our load that we're driving it, so if we're just looking at the mid-band region, the load that we're driving is R sub L. And we can open circuit our capacitor then. So what we have is that in the mid-band region, the gain V out over V signal is just going to be RL prime divided by RL prime plus RS, where RS is equal to 1 over GM. RL prime in this case is the total impedance we see at this node here to ground, in which case we see RL, and we also see the R naught of the transistor. So we also see R naught of the transistor. So R naught in parallel with RL becomes the driving load that this source follower has to drive. So we have that RL prime is actually given by this RL in parallel with this R naught here. So RL prime is given by RL in parallel with R naught. So that's how we can find our midband gain. And so then we can draw our small signal model for the rest of the transistors in order, the rest of the capacitors, in order to see the overall high frequency response. So we can see then with all of these capacitors not here, this would just be the circuit I was just discussing, and the midband gain would just be RL prime equal to RL in parallel with R naught, and the gain would just be RL prime divided by RL prime plus R signal. Now, when we add these capacitors in, what we have is we have the gate to source capacitance. So this gate to source capacitance down here. We also have the gate to drain capacitance, which would be up here. And then finally we have, the load capacitance, which is just shown here. Now the load capacitance would include, if we have the source to bulk capacitance here, the load capacitance would include that C source to bulk would be should be really included here, and would add on to CL, but we're not taking into account in this particular case, but that would normally be taken into account, would be included. So what we find then is that we have two nodes. We have a node here and we have a node here. So we'd like to, this node is already connected to ground, so C gate to drain is already connected to ground on one side, but this is now the capacitor which is not connected to ground on one side is now C sub GS, the gate to source capacitance. So at first glance we might say, well, we can use a Miller effect and break that up into two capacitances to ground. Turns out it's not a very good estimate in this case because the gain from the gate to the source is approximately equal to 1 or a little less than 1, and so it doesn't give a great estimation on what the high frequency performance is for this circuit. So it turns out it's not too difficult to find actually the impedance looking across C gate to source, just working out analytically what that impedance is, and then using that for the high frequency pole due to C sub GS. So this just talks about what I was mentioning. The Miller theorem tends not to give a good estimate in this case because we have V out approximately equal to V sub S. So we have these three poles due to the three different capacitors, C gate to drain, gate to source, and CL. Let's talk about the one that's the most troubling one, which was the C gate to source here. So as I mentioned, what we can do though is we can actually just find R sub GS. So R sub GS is the impedance seen across CGS just through analysis. And I'm not going to show the analysis here, but if you do the analysis, you'll find that this ends up being the impedance seen across for that. So you just have to do nodal analysis in this particular case. So this would normally be in a table lookup because it's not something you would just like to do every time that you have a circuit. So it turns out to be just R sub signal plus RL prime divided by 1 plus GM RL prime. And that's equal to the impedance of the resistance seen by capacitance CGS. So if we take that then and multiply this times CGS divided by 2 pi as well, we end up with the high frequency pole due to CGS. Now the other two are more straightforward. The other two we have C gate to drain. So we have this capacitance here. We say what impedance does this capacitance see? And when the other capacitances are open circuited. And so in this case it will just see R sub signal. So we have that due to FP1, it's just equal to C gate to drain times R signal and divided by 2 pi as well. Then we have for CL, the resistance that we see across here is just going to be RL in parallel with R naught. So if we, oh actually sorry, I forgot to include one more, so it's going to be the impedance we see looking into RL, into R naught, but also the impedance looking up into the source because of this voltage controlled current source looking into the source of the transistor. Or in other words, this CL is going to see RL looking down, it's going to see R naught looking up, but also looking into the transistor source as well. And looking into the source of the transistor we've already seen is equal to 1 over GM of that transistor. So we have that for CL, it's just equal to RL in parallel with R naught, also in parallel with RS, where RS is equal to 1 over GM of the transistor. What you find that in this in this source follower case is that all three of these poles are generally higher than in the common source case. So in general, what you find is a source follower tends to be a faster circuit. It's not as limited as it is in the common source or the common gate cases. But of course, it has no gain. The problem with that is that we saw that the gain is that just equal to a resistor divider. So the gain is always less than 1. So you can't get a voltage gain of this at all. You do get a power gain because the current gain here can be large, but the voltage gain is always going to be less than 1. So it does get used when you need to drive a lower impedance. So if you're trying to drive a smaller impedance, then a source follower is a good way to go, but it doesn't give you any voltage amplification, and you need to use a common source or a common gate in order to do that. And that ends this video. Thanks for watching.